All right, Math 2, here we go. We got lesson 4.1.1, introduction to factoring expressions. So we're going to start into factoring, which is a really important skill that you're going to need pretty much for any math, continuing on. If you continue on to any math class, you're going to need to know how to factoring. Factoring is basically unmultiplying or undoing the distributive property. Okay, so we're going to kind of look at this and see if we can figure out what's the best method to factor. We'll just introduce it today, and we'll go a little bit deeper on the next few lessons. So anyways, we've got this algebra tile thing over here. We've done these before in class. So we want to write this as a product equal to a sum. Remember, a product just means that we're going to do length times width. So we're going to find out the length and then the width. And the sum is when we add up all these individuals over here. So if this is xy and this is x squared, so this must be the x and this must be the y right there. And then this is x times x to get x squared there. And then this must be x times 1 to get that there right there. So let's see, this is x and this is a 1 because x times 1 is x. So this must be a 1 right here because y times 1 is y. That's a y. Oops, that's not a y. That's an x. Not bad. That's a y. That's a y. That's a y. That's an x. That's an x. That's an x. 1, 1, 1. Because we got 1 times y to get y there. 1 times y. 1 times y. And then 1 times x, 1 times x, 1 times x. Anyways, these last boxes are just unit squares, so these are just ones over there. All right, so looking at this entire side right here, I've got x and 1, 2, 3, 4. So that side would be x plus 4. Looking at this side, I've got y and an x and 2 singles. So that would be x plus y plus 2 singles. So that is written as a product where we're multiplying the length times the width of that rectangle. Writing it as a sum, we would just take all of the like terms and combine them. I've got an x squared, just one of them. So 1x squared or just x squared. I've got an xy. There's just one of those. So plus 1 of the xy's. I've got 1, 2, 3, 4 x's. I've got 4 of the y's. And I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 singles. Ooh, I didn't plan that out very well. But anyways, there we go. All right, so this is written as a product. This is written as a sum. We've done this a lot. You did it in Math 1 as well. All right, multiply using the area model. So we've got 6x minus 1 times 3x plus 2. So that's written as a product. We're going to try to turn it into a sum. So we do the area model. Yay, there it is. I made 4 boxes because I'm going to put a binomial of 6x minus 1 on one side, and I'm going to put 3x plus 2 on the other side. You can put it on the top or the bottom. It doesn't matter. Let's put it on top. All right, so this box, this area right here is 3x times 6x. That's 18x squared. We've got 3x times negative 1 here. That's negative 3x. This box would be 2 times 6x for the area. That's 12x. And the final box is negative 1 times 2. That's negative 2. We have like terms in the peanut right there. So I've got 18x squared. These two combined, they're like terms. 12x minus 3x is 9x minus 2. And so now we can see that 6x minus 1 times 3x plus 2 is this trinomial sum. 18x squared plus 9x minus 2. All right, so we also played around with algebra tiles in a previous course. I think we even did them earlier in this course. But when we try to do these algebra tiles, we try to turn them into rectangles because then we can get a length and a width from it to get it into a product and a sum. So this first algebra tile that we're going to look at is 2x squared plus 7x plus 6. So that means that I've got 2 of these x squareds. So we're going to say these are x squareds. So I got 2 of them. I can put them on top of each other, or I can put them on the side of each other. I'm just going to put them on the side of each other. And then we've got 7 of these single ones, right? These are the x times 1 on this. Oh, that's 6. There's 7. So I need to put them in such a way. Let's maybe put one over there. How are we going to do this? Yeah, let's do it like this. Is that going to work? Wait, that's only 1, 2, 3, 4, 5, 6. Oh, I need more. All right, that's why it wasn't working. I didn't count everything out correctly. So I could put this one right here, or I could move these two up here. It looks like it would work either way. No, it won't work that way because there's only room for 1, 2, 3 singles. So I'm going to have to put it over there. And now I've got 1, 2, 3, 4, 5, 6. There's my 6 singles. 1, 2, 3, 4, 5, 6. All right, there's my rectangle. So again, we started off with 2x squared plus 7x plus 6. So that's what I started off with. So here's my 2x squareds. I've got 1, 2, 3, 4, 5, 6, 7, 7 of the x's, and I've got 6 singles. And I was able to make this into a rectangle. This side of the rectangle is x, and this is a 1, and this is a 1. So that's x plus 2. This side is an x, a 1, and a 1. So that side would be 2 of the x's plus 3. So now we can see that if I have 2x squared plus 7x plus 6, I can turn it into a product of x plus 2 times 2x plus 3. This is actually what factoring is. It's turning like a polynomial like this into multiplication. This is what factoring is. And it's really useful down the line when we go deeper into math. It'll be even pretty useful this year. Okay, so that's what factoring is. So what you do is you take your parts, you change them into a rectangle, and you can just do length times width and then turn it into a product. All right, so that's the first one. The second one on the piece of paper that we had was x squared plus 4x plus 1. So in this one, I've got 1 of the x squareds, 4 of these x's, and then 1 single. So at this point, I need to turn this into a rectangle of some sort. So if I put them there, so there's my x squared, my 4x's, but then I have just plus 1. So I'm missing 3 to turn that into a rectangle. Well, what if we move them around? Let's move it up here. Now I'm missing 2 to turn it into a rectangle. Okay, what if I put it up here? Nope, still not working. Now I just got this floating single and I'm not making a rectangle. So having an x squared, 4 of the x's, and a single 1, it doesn't look like I can turn this into a rectangle. So not every polynomial can be turned into a rectangle when we're playing around with the algebra tiles. What we're going to find out that means is not everything that we get can be factored nicely like all these parts that we're doing. All right, let's get back to the other thing. Let me pause this. All right, back to where we were before. So we found out that this one I was able to turn into an area model where I ended up with having x plus 2 on one side and 2x plus 3. So we turned this polynomial into a product of 2 binomials. This one we weren't able to turn into a rectangle. So not every expression, polynomial expression, can be turned into a rectangle. And when we can't turn it into a rectangle, we're just going to say that it's not factorable. We also call that prime. All right, moving on. So that's basically what factoring is, but we're going to have to kind of set up some ideas in order to get us ready to factor. because we're not going to be able to walk around all the time with a bunch of algebra tiles to do this. It's probably the least efficient method for doing factoring. So we're going to try to come up with a efficient method for factoring, and what we want to do first is try to look for patterns. So here I've got an area model problem. So I'm going to find out what the product is. So I've already got the sum right here. Well, most of it. I'm going to write the product. So this is 6x to the second, and that's 2x. So I think this should be 2x, and this should be 3x, because that's how I get 6x squared. And then 2x times what equals 2x? 2x times 1 equals 2x up there. All right, and then 3x times what equals 15x? Well, 3x times 5 equals 15x. And then I can see that 1 times 5 does equal 5, so everything's working out great. So written as a product, the product would be 3x plus 1, that's the length right there, times the width of 2x plus 5. So that's the product. The sum would be 6x squared in the peanut right here. It's a weird peanut. We got 2x and 15x, those are like terms, so we'd say plus 17x and then plus 5. So written as a product, written as a sum. Okay, this one, 5xy. This part has y's up there, this part has x's over there. So this is going to have x's here, and this is going to have to be y's here. That's 5, so I can't put the 5 here because I'm not going to multiply and get -2. So I'm going to put the 5 over here, and this will just be y. So 5x times y is 5xy. Then something times y equals -2y, so this must be -2, because -2 times y is -2y. Then 5x times something equals 15x, that must be 3. And then 3 times -2 is -6, looks like it's working. So my product is 5x minus 2, 5x minus 2 times y plus 3. My sum is where I combine my like terms. Oh, there are no like terms. These are all different terms, so I just write them all down. 5xy plus 15x, 15x, minus 2y, minus 6. Last one of this set. So here I've got a 12x squared. So 12 can be like 2 times 6. It can be 3 times 4. It can be 1 times 12. It can be a lot to get 12. But I'm looking at the numbers, and I think this needs to be 3x right here. Because if this is 3x, then I think it's going to work out so that I can get -3 here. So 3x times -3, that's -9x. That means this one has to be 4x, because 4x times 3x is 12x squared. All right, so working this way, so 4x times something equals 16x, this must be 4. So 4x times 4 is 16x, that works, and -3 times 4 is -12. Everything is right in the world. So as a product, 4x minus 3. As a, over here, 3x plus 4, sorry. And as a sum, we would combine our like terms, and in our little peanut right there, we've got our like terms. So -9x and positive 16x, so I'm starting at 12x squared. -16x, or positive 16 minus 9x, that should give us a total of 7x. And then minus 12. All right, there is a pattern between the diagonals of the area model. Okay, so if I'm looking at the diagonals, 6x squared and 5, 2x and 15x, there's actually a pattern there. If we multiply our diagonals, 6x squared times 5, that's 30x squared. The other diagonal is 2x times 15x. And that also equals 30x squared. So that's a pattern going on. The product of the diagonals equals each other. Product meaning the multiplication. Dang it, stupid lights! So the product of the diagonals, so when we multiply the diagonals, wonder how many of these videos the lights go off. Probably most. The product of the diagonals equal each other. All right. Now look at all these problems. Does that pattern hold up? Let's see. 6x squared times 5, that's 30x squared. 2x times 15x, we just did this problem. Yeah, that works. Let's look at the other ones. Negative 6 times 5xy, that's negative 30xy. Negative 30xy. Negative 2y times 15x, is that negative 30xy? It sure is. 12x squared times negative 12, that's negative 144x squared. Negative 9x times 16x, yep, that's negative 144x squared. So yes, the pattern seems to always work. The diagonals, when you multiply them, always equal each other. And we're going to pick up on that concept on our next lesson. All right, see you later. Math hard. Bye-bye.